Okay, welcome everyone. I'd like to talk today about Khovanov-Rozansky homology, specifically Khovanov-Rozansky homology of torus links. So the motivation for what I'm going to talk about today is, so we have these homology theories for links these days. For example, Khovanov homology and its various cousins. These are powerful link invariants, but it's also important to have ways of computing them. So for things like Khovanov homology, we actually have computer programs that work pretty well. But for various relatives of Khovanov homology, for example, what I'll focus on today is this triply graded version of the Khovanov-Rozansky homology. This is the version that categorizes the Humphrey PT polynomial. For this link homology theory, it doesn't really lend itself very well to computer computations, not at the moment anyway. One reason is because the homology of a link in this case is essentially always infinite dimensional. So it'd be like finite dimensional in each grading, but there's infinitely many gradings to worry about. So this is the sort of thing that maybe computers aren't very well. Anyway, we haven't taught to my knowledge, we haven't really taught a computer how to compute this yet. So it is important to be able to compute these things by hand if possible. Surprisingly, maybe perhaps miraculously, this is actually possible. That's one of the themes of this lecture. Basically introducing a method for computing this particular homology theory, but the same ideas will apply for other homology theories as well. One of the reasons why you might specifically care about torus links is this circle of conjectures by various subsets of these authors, relating, say, Khovanov-Rozansky homology of torus links to things like Hilbert schemes and rational Chrednik algebras and so on. I don't really want to say anything about these conjectures, but they're very interesting, and if you're going to try to approach them, you had better have some way of computing on the topological side. You better have to have some way of computing the homology of these torus links. So these conjectures don't concern specifically torus links, but torus links are certainly the most prominent main characters in these conjectures. Which, by the way, we now have proofs of based on this technique for torus links, or for torus knots anyway. The original motivation for considering this particular technique that I'll be talking about was me. So Ben Elias and I had been thinking about the problem of diagonalizing the action of the full twist braid acting on the category zirkel bimodules. And the proof of this, that this action is categorical, is diagonalizable in a categorical sense, involves knowing something about the braid closure of the full twist, which is the NN torus link. Okay. So this lecture is separated into two parts, two videos. The first part that you're watching now is all about this technique of me and Ben for computing or approaching the computation of Khovanov-Rozansky homology. And the second part is the application to torus links. The applications to torus links were worked out in various cases by subsets of me, Ben Elias, and Anton Mellon. So I'll say more about that in the second video. The strategy for computing is going to be very much skein theoretic in flavor. So I want to begin with just by recalling the usual skein theoretic definition of the Humphrey PT polynomial, so the decategorified story. So we have these formal parameters A and Q, these Humphrey parameters. We start with a link diagram, which for us will always be presented as the closure of a braid. So that's not really essential at this point, but when we categorify, we'll have to restrict to braid closures. And to get the normalizations to match, we'll make that restriction here as well. So we have the skein relation for the Humphrey PT polynomial. It looks perhaps different than you would expect or than you're familiar with, but I promise you it is the usual Humphrey PT polynomial up to a normalization that depends only on the rise, not just the rise of the diagram, but also the number of strands of the braid. So this asymmetry between positive Reidemeister 1 and negative Reidemeister, sorry. Oh, look at that. I have a typo. The asymmetry between the negative Reidemeister 1 and positive Reidemeister 1 looks maybe a little offensive at the beginning, but just keep in mind that the normalization that we take depends on not just the rive, but also the number of strands. So you can fix this asymmetry with some normalization. Okay, and then another kind of offensive thing that you might notice is that our parameter a here could really probably be called negative a squared, just based on what is the invariance of the unknot. But that's minor, and we are not going to do it. Just a silly change of variables. Okay, so these are the conventions that we'll use. Now, it will be beneficial to consider not just braid diagrams or length diagrams and things like that, but allow arbitrary, like formal linear combinations of braids and links. So, for example, we consider a vector space formally spanned by all braids of a fixed number of strands, modulo the skein relation, we get an algebra called the Heck algebra. And so, in addition to considering things like braids and braid diagrams, we can also consider braid diagrams decorated with Heck algebra elements inside them. And those have concrete meaning in this game theory world. So specifically what I want to consider are these symmetrizing elements defined here. They're like unnormalized versions of these symmetrizers. So on n, and then they'll be indicated diagrammatically as just like a shaded box with some number of strands entering and exiting. So on one strand, the symmetrizer is not the identity, but it's this rescaled version. And on n+1 strands, the symmetrizer on n+1 strands is defined in terms of the guy in n strands using this identity. Precise form doesn't matter, but there it is. I mean, it's not relevant to memorize this right now, but it's an exercise to show that these elements that I've just defined really are symmetrized. So the symmetrizing property is expressed here. These boxes absorb braids with, in fact, no. So in these normalizations, there's actually no additional factor there. And in order for these things to be sort of useful in the computation of the Homolgy-PT polynomial, we need to know how they interact with the process of taking braid closures. And so that's illustrated in this last line. The sort of trace of the n+1 symmetrizer is a scalar multiple of the n symmetrizer. Okay. A partial trace, I should say. Now, these are unnormalized versions of the symmetrizer in the sense that they are not idempotent. They don't square to themselves. So they're like scalar multiples of a symmetrizing idempotent. But these particular scalars are going to be important for the categorification later. Okay. And now how these guys get used in practice for like computing the Homolgy-PT polynomial is sketched here. But first off, if you have a diagram with no symmetrizers on it, then you can always take isolate your favorite place on the diagram and use this identity. So the identity on just like one strand can be rewritten as a symmetrizer on one strand with this prefactor. And once you have a symmetrizer, this recursion relation, after you rearrange this recursion relation a little bit, you end up with this linear relation. So if you ever see a strand passing entirely below a symmetrizer, then you can exchange that for a strand passing entirely above that symmetrizer, plus a term with a bigger symmetrizer. So, switching all these crossings has the potential of simplifying the diagram if you switch crossings in an auspicious way. And having a larger symmetrizer also has the potential for simplifying the diagram, because a larger symmetrizer will eat more crossings. So we'll see how this gets used for torus links in the second video. But this is sort of roughly what it looks like, what the strategy is going to look like. So we have not only the usual skein relation that allows us to switch positive crossings and negative crossings modulo lower terms, but we have this extra kind of version of the skein relation, which is like we can switch a positive crossing and a negative crossing at the expense of introducing a little symmetrizer. And the symmetrizer can be helpful to have symmetrizers around. Okay. So when we categorify, so consider Khovanov-Rozansky homology. The way this looks is so you start with a braid. So you start with a braid representative of your favorite link. There's a construction due to Rouquier, which will produce a chain complex of Zergel bimodules. So I'm not going to tell you what is a Zergel bimodule. It's just some kind of category of objects, and this Rouquier tells us how to associate a complex in this category with each braid. Now there's a functor called Hochschild cohomology, which, given a complex of Zergel bimodules, will produce a complex of vector spaces. Once you have a complex of vector spaces, you can take it's just homology in the usual sense, and you end up with a vector space. And composing these is what defines Khovanov-Rozansky homology. You start with your braid, you form the Rouquier complex, you take the Hochschild cohomology term-wise of that complex, and you take homology of that, and you get Khovanov-Rozansky homology. If you notice, I said these were not just complexes, but these were triply graded complexes and triply graded vector spaces. So let me tell you what are the three gradings. So first off, because these were complexes of Zergel bimodules, we have a cohomological grading, E grading. These bimodules were in fact not just bimodules, they're in fact graded bimodules over a graded ring. This Q represents the grading inherent to those bimodules. This last grading appears once you take Hochschild cohomology. So this is the Hochschild grading. Okay. And just a word of warning, it can be confusing, and with very good reason. The word cohomology appears twice here. So we have the homological, we have the cohomological grading of just complexes of bimodules, and we also have the grading inside Hochschild cohomology. And you should think of those, well, they are two independent gradings. So I'm not mixing those up. We have the homological grading of these complexes, and then the grading of this Hochschild cohomology. So one of those is T and the other is A. None of these details are going to be extremely relevant for us because of the technique for computing, or the sort of method that we're going to be using to compute things. We'll actually not really need any of the details of the construction. We won't need to know anything about Hochschild cohomology or anything about Zergel bimodules. I promise. It's really just essentially combinatorics in the end. Now, quickly, how does this homology theory relate to the Homoley-PT polynomial? So we have these three gradings, Q, T, A, and if you take the direct sum, or if you take the sum of dimensions of these homology groups, weighted with powers of Q and A, i.e. specialized T equals -1, you get exactly the Homoley-PT polynomial. So this version of the Euler characteristic recovers the Homoley-PT polynomial from the Khovanov-Rozansky homology. Okay. I guess that's all I want to say. Okay, so we want to use intuition from skein theory to be able to discuss chain complexes and manipulate them, and eventually on the next page, basically the technique for computing things is going to use skein theoretic language, So in order to bring that into the picture, we have to have diagrammatic language for discussing complexes of bimodules and various operations we can perform on them. So we have the category of Zorgel bimodules. Just like the Heck algebra, this depends on the parameter n, which is the number of strands in our braids. So if you start with a complex of Zorgel bimodules, we'll just denote that diagrammatically by a formal little box labeled by X. So if the complex is called X, then we'll indicate it diagrammatically by a box labeled by X with n incoming strands and outgoing strands. Because these things are bimodules, there is a tensor product operation on them, much like the multiplication in the Heck algebra or braid group. This will be denoted diagrammatically just by vertical concatenation. And then there's an operation called external tensor product, which increases the number of strands. We'll denote the operation of taking Hochschild cohomology by this trace-like operation. So given a diagram, you just kind of connect up all the strands in a plane, and that will be our just notation for taking Hochschild cohomology. Finally, there is a categorical analog of the symmetrizing element inside the Heck algebra. So this will be denoted by just, again, exactly like in the decategorified situation, just a shaded box with n incoming strands and n outgoing strands. So this denotes the symmetrizing object Kn that was constructed by me earlier. Okay. Just to illustrate how some of this stuff gets used in practice, here we have a diagram, color-coded various parts of the diagram. So on the top, we see a braid. That braid represents a chain complex, namely the Rouquier complex of that braid. On the bottom, we see a symmetrizer and an identity. Anyway, and so the operation of vertical concatenation is this tensor product of bimodules. And then this horizontal concatenation or horizontal kind of juxtaposition is this external tensor product. So the complex represented by this diagram could be written in like more traditional language as so, but we'll very much prefer the diagram. It's much more compact, and we can use, I don't know, the intuition from skein theory to think about things. Okay. And I guess also the closure of this diagram just represents Hochschild cohomology of that complex. Okay. So the relations that we're allowed to use, this theorem here represents the technique that we're going to use for computation. So these complexes, which are indicated by these diagrams, satisfy the following relations. So first off, we have the usual things, so like braid invariance of Rouquier complexes, and Markov II invariance of Rouquier complexes. This is the sort of thing that you need to prove in order to have that Khovanov-Rozansky homology is a link invariant. And the analog, okay, and then we have the more interesting relations, the ones that involve the symmetrizer. So if you see a strand, anywhere in your diagram, you can replace it up to homotope equivalence by some infinite direct sum of guys that have the symmetrizer on one strand. And with shifts, these are just shifts in the Q degree. And these red arrows represent additional terms in the differential that you have to add. So remember, each one of these little diagrams is possibly part of a larger diagram with its own big differential. There's some differential internal to each summand, and the total differential on this thing is the direct sum of the sum of all of those differentials internal to the summands, plus some component of the differential indicated by these red arrows. And there's infinitely many terms, infinitely many red arrows. Okay, so that's their first relation. If we wanted to, we could indicate this with some shorthand. This is just like an infinite direct sum of many copies of this symmetrizer on one strand with some internal differential, and we could indicate it kind of somewhat abusively by this notation. I would say the most important relation is this recursion relation that tells us how the symmetrizer on n plus one strand, n plus one strands is related to the symmetrizer on n strands. So if you see a symmetrizer on n strands with another guy linking around it, that whole complex is homotypical to a direct sum of two things. The first summand has a bigger symmetrizer, and the second summand and there's an extra component of the differential, but you should think of this as this chain complex split plus an extra term in the differential. So technically speaking, what I'm indicating here is one-sided twisted complex. So what it means is it's a direct sum. Turn on an additional component to the differential. Additional component to the differential is sort of strictly increases some part. Mapping cones, iterated mapping cones, and really I just want to think of them as directs of the where you kind of turn on an extra piece of an extra term in the differential. Okay. Finally, so we have the symmetrizing complexes behave as symmetrizers or braids of the homology. And finally, they interact with functional cohomology. My video is not updating. Okay. So this interacts with homology as in this relation. So there really is no additional difference. This is an honest direct sum. There's no differential relating the two terms. And finally, Hogancamp cohomology of a tensor product doesn't matter in which order you took the tensor product. So this is important for proving like conjugation invariance of Hogancamp cohomology, of Khovanov-Rozansky homology. So this is a Markov 1 invariance in disguise. Just to illustrate how these relations can get used in practice, here's one way of rewriting the full twist, the Rouquier complex of the full twist braid. You start with the complex associated, so you start with the full twist, the braid diagram for the full twist. Introduce a symmetrizer on one strand. So this is now a big infinite direct sum of many copies of this diagram with shifts and some additional, there's differential internal to each guy. Each guy here is a Rouquier complex, so it has its like own differential. And then you introduce new terms of the differential which point to the right. Again, I haven't told you what these differentials are. The thing you'll have to take on faith, and we'll see in a moment, is that we actually don't need to know what these differentials are explicitly, ever, in this talk or the next video. Anyway, so if you have the full twist on 3 strands, it splits as a direct sum of infinite many copies of this one complex. So we focus on this guy. If you ignore the blue strand, then you see a complex to which we can apply the recursion, and the result is this 2-term twisted complex. Each term in this twisted complex can itself be simplified using the recursion. Okay, so this first term gets rewritten as a direct sum of 2 things with differential. This second term gets rewritten as a direct sum of 2 terms with differential. What I'm doing here in the second guy is if you want to think about it this way, I'm focusing on this part of the diagram and I'm applying the recursion there. But anyway, so this sort of technical thing that I'm using here is called homological perturbation theory, which tells us that if we have a mapping cone, or in general a one-sided twisted complex, or whatever, we can take the terms of that mapping cone, that is to say, in this case, these two complexes, and each term we can replace by anything homotopy equivalent to it. So this one term becomes 2, this one term becomes 2, and that replacement can be performed inside the larger twisted complex. The differential, now what we can say about the differential which is already there, so like we had this differential relating those two terms, and it sort of induces some differential on the result. We don't know very much about it at this stage because I haven't really told you anything about it. And then the situation becomes only murkier once we go anyway. But the only thing that we know about this differential is that it points to the right. In fact, that's the only thing that we're going to need to know about the differential. So you have the differential. Anyway, okay. So, sorry, I just want to iterate. So this is some description of the full twist complex. It's homotopy equivalent to a direct sum of 4 terms. And some differential, some additional piece of the differential relating those 4 terms. And I promise the only thing that we're going to need to know about this differential is that it's strictly increasing with respect to some partial order on these terms. So it maps you from, anyway, it maps from the right, or it maps in the sort of south or east direction. Okay, I just want to conclude with an example of the trefoil, how to actually use this technique to really compute the homology of the trefoil. So again, the first step looks very similar to what we had before. We have a diagram with no symmetrizer on it. We introduce the symmetrizer. Each term in this big direct sum, we focus our attention on it. We see a place where we can use the recursion. We do so, and the result is this 2-term twisted complex there. The first term, that crossing gets absorbed by the symmetrizer. The second term, we have positive Reidemeister 1 that we can use. So that disappears. Okay, and again, those replacements, excuse me, those homotopy equivalences are sort of, we're using homological perturbation theory there. We've simplified the terms of a twisted complex. And this is a valid operation. The differential, anyway, there's some differential on the result. It points to the right. Okay. Anyway, and now we can simplify each of these terms further. We say 2 applications of this Markov move for symmetrizers produces that factor. 1 application of the Markov move for symmetrizers produces that guy. And then there's some potentially mysterious differential on the result, indicated in this like pinkish arrow. So in conclusion, what we have for the trefoil is we have the complex which computes the homology of the trefoil is homotopy equivalent to some complex whose underlying vector space has this graded dimension. So the denominator there comes from this geometric series representing this direct sum with shifts. The thing to observe here is that the homological degree always, you only ever see even powers of t anywhere. And so whatever this complex is, it's supported in even homological degrees. So the differential is 0 for degree reasons. And so actually we have computed the homology of the trefoil. So the homology of the trefoil in the end is isomorphic to the complex vector space with this guy has his graded dimension. Okay. Okay, so this is it should remind you of how you compute homology of things like complex projective space. You don't actually need to know the definition of singular homology or whatever. You just need to know that complex projective space has a CW decomposition with only even dimensional cells. This is very similar to that. And this is the same exact idea that we're going to use to compute homology of all positive torus links in the next video.